Well, good evening. It's the 23rd of March, 2022, and I'm Charles Schultz with the Randomizer. And tonight's concept is a simple yet perplexing one, and that's gravitation, the one force that refuses to be unified. We're going to talk about gravitation tonight, and we're going to see some of the things that it implies and just talk about the theory and practice of analyzing forces and the transfer of momentum in nature. So before we get into it, I'm going to encourage everyone to go to schultzlaboratories.com or universesciencecenter.com, visit our site, walk through our 3D galleries and our virtual learning space, and see what's in there for you. Get your Oculus or Vive or other 3D headset and enjoy it. If you happen to have a skill you wish to teach or a specific discipline you're an expert at and you want to share it with the world, get in touch with us and we'll set up a classroom or gallery for you so you can do it in virtual space and reach many, many more people than you would one place at home, for example. Also, we encourage you to become a member of schultzlaboratories.com or universesciencecenter.com and support our growth and additional new galleries we're working on. There's always something new coming. And remember, every weekday at 6 p.m. Eastern Standard Time, we have the Randomizer, where we select a new random technical term and talk about it. And 9 p.m. Mondays only Eastern Standard Time, we're going to be resuming our lessons very shortly. Schedule will be posted very shortly so you can see what's coming up. And it's a runoff between robotics and math and music. So it's going to be fun, whatever we do, and I hope that you choose to attend. Join us for those meetings. So off we go with gravitation, a curiously attractive sort of discussion. So gravitation is one of the four fundamental forces in our universe. And to quickly go through them, we have the strong nuclear force, which binds the nucleons together to make the nuclei of atoms. And then we have the electromagnetic force, which we recognize as light, radio waves, microwaves, X-rays. Then we have the weak nuclear force, which is very similar to the electromagnetic force, but much weaker and only occurs near the nucleus, in the nucleus, and with certain classes of particles. And then finally, we have gravitation. Now, physicists for many years have been fascinated with something they call the theory of everything. And in the theory of everything, we're able to take all of the forces and all the particles and make one simple set of equations that describes it all. And one of the steps is to find the similarities and differences and see how we can unify those things into one concept. Well, at this point, they have what they happily call the theory of almost everything. And it isn't exactly what they thought, but it's getting close. And the one holdout in unifying the forces is gravitation. So when we study the very early moments of our universe, we find that the temperatures and pressures were incredibly high, things that we can only barely begin to approximate in some particle accelerators today. And when we're looking at those conditions, we discover a very curious fact. At high enough temperatures, all of the forces seem to unify into one superforce that influences everything uniformly. So all particles of matter that are influenced by these forces would all be equally influenced by them. Right now we have particles that are influenced like just by the electromagnetic force or just by the strong nuclear force. All of that would merge together and all possible particles would be influenced by all of the forces pretty much equally. And then a curious thing happens. As the temperatures drop, as the universe expands and cools, there's something called symmetry breaking. All the forces are considered symmetrical at that time, where they all fit together. And at symmetry breaking, the forces split apart and veer off and go their own way. They assume their actual working force or strength that we see in common throughout the universe. So gravitation, it is theorized, was the first force to peel off of this set, and then after that, the electromagnetic and weak nuclear split aside from the strong nuclear force, and then they claved apart and became separate forces. So now we have four fundamental observed forces in our universe that we understand and can measure. And each has been studied well enough to understand its characteristics, where it works, what environment it requires, what particles it affects, and what it does. In a nutshell, one thing is done by all of the forces, and it is to transfer momentum. So if you imagine one object striking another object, if they were in free fall, one would transfer its movement, its momentum to another and would recoil in some way. And so the force of movement, the energy of its movement, its momentum, can be transferred into another object and cause it to move. And so we know very, very precisely how this works. And for solid objects, it's easy to understand. The solidity of one object is an illusion caused by repulsive forces from electromagnetism. And these objects don't merge because the repulsive forces are strong enough to keep them from intersecting each other. When one object carrying momentum, strikes another, it transfers it to it mechanically. And so that's easy to see. If you play pool, one ball will strike another and it will ricochet off into another direction. And you can calculate with great precision, just visually with practice, where those balls will travel. The same is true for planets in orbit. The same is true for spacecraft flying through space. We can calculate those forces very distinctly and very easily. When it gets tricky is when those forces are carrying momentum in ways that trick you. Sometimes it's with rotary or rotational momentum, and sometimes it's with flexing. The energy can be stored in a flexible medium such as a spring. But when we get to gravitation, we discover something very, very odd. All of the forces that interact with things transfer positive momentum from one thing to another. And we can see this illustrated when an electron repels another electron. The electromagnetic force carries the momentum from one to the other and allows them to move apart. And that's easy to understand and to predict. When we get to gravitation, we find that it's the only force that is unipolar, doesn't have a plus or minus, it just has a yes. And the other thing that it has is that it draws things in, both the source of the gravitation and the object being acted upon pull themselves together. If you do the math, it's very clear that gravitation carries negative momentum. And that's a very curious thing. And that is one of the reasons that it does not unify with the other forces. Now, in reality, that might sound like an inaccurate statement. It's really based deeply on the physics and mathematics and some things we still don't fully understand. And that's a thing that really irks physicists. Some take great offense to the fact that they don't understand a thing. Others look at it as a challenge. I tend to see it as a challenge. Gravitation has a very curious beginning. When studies were made of momentum and inertia and how it is coupled to matter, there was a fellow who theorized the existence of something called the God particle, as it's called. And this is the one that couples the momentum, the mass, to an object. And so this particular particle was only recently verified in accelerator experiments. It was found in the collision debris of particles. Well, if you think about it, something has to give mass to matter, but it tends to be something elusive. We've been very unable to describe exactly what inertia and mass are, except for mathematical constants. We simply see matter and know that it has those properties. Gravitation does something very interesting. Because it is very, very weak and it only has one pole to pull, it is cumulative, and the force of gravitation can literally stretch to the ends of the universe. So the mass of our star moving around influences all the stars around it all throughout the galaxy, and in some ways all the way to the end of the universe. So mass has a field, gravitation, that does not die out entirely. It literally just gets weaker and weaker all throughout the universe. Now, one of the things that's very, very interesting is this. We know that objects with mass literally bend space-time. They distort the space-time. And it is almost as if you had a sheet of rubber and you dropped something heavy on it like a ball and it dimpled down. Well, that curvature around it is very similar to the curvature that the space-time itself would have. Well, what makes this happen? That is the whole mystery of the Higgs vector boson, this God particle I mentioned earlier. And Peter Higgs, the fellow who came up with it, did some math, came up with this theory, and did in fact predict the particle that did show up. But how it works is another method of madness. It's something that drives people crazy. They don't understand how this particle couples the mass into something. But something that I have noticed is this. When a planet is orbiting a star, we expect that the exchange of information from the gravitons holding that planet in orbit would move at the speed of light. All right, that seems reasonable, and we can measure the speed of gravitational waves, and they do indeed travel at the speed of light. But if the force of gravity itself moved at the speed of light, we would run into a real problem very quickly. Imagine the Sun and Neptune, which is about 5 light hours away. The speed of light, a signal would take 5 hours to reach Neptune from the Sun, and vice versa. If the force of gravitation propagates at the speed of light, then these bodies are in movement, and Neptune would be pulled by a source of gravity that is no longer where the Sun actually is. It will have moved. And the Sun will be pulling on a planet that is no longer where it was. It would be moved. So how does that not make the orbits fall apart or spiral into each other? The answer is actually very simple. The force of gravitation does not literally emanate from the body itself, from its mass, but rather from the space-time curvature around the mass itself. So imagine when you pull a spring and you hear it creaking, when you're stretching it out, or pulling a rubber band and you hear it stretch. What you are doing is you are creating a release of energy in the release of noise or heat when you stretch that object. What if the structure of space-time, when stretched, would react by giving off a cry of negative momentum, the gravitational force itself? This solves the issue of decaying orbits, because this star and this planet are not pulling on each other. Rather, the bowl of space-time, dimpled space-time around them, is already contacting that dimpled space-time, and they're interacting out here as a whole object that's as wide as a solar system. So now there will not be a missed source of gravity due to the delay of travel time for that signal of gravitons. Instead, the two bowls are moving around each other. The bowls are doing it, not the matter itself. Now this also solves another mystery. What the Higgs appears to be doing is coupling the mass to the curvature of space-time. Now, if this is true, then it solves a couple of interesting issues, but it also raises some others. Perhaps the reason we're not unifying the forces is because gravitation itself is fundamentally and quantitatively different from the other three universal forces. That makes a lot of sense. If you treat gravitation as a geometric entity and the graviton itself as a reaction of the space-time to being distorted, now you're getting close to something that you may be able to unpuzzle, because now you look at it from a different viewpoint. It is the space-time itself that's doing it, not the mass. Now think of it like this. What if you could take a picture of somebody shooting a BB pistol at high speed, and you could see the BBs coming out and you could see the recoil? Now you could see exactly where the particles were coming from. But what if the person was surrounded by a cloud of BBs and their stretching the space released the BBs? This is a completely different model, and it gives you kind of a visual image of what could be happening. And remember, everything that happens at the quantum mechanical level at some point. We often treat masses and particles and forces as points or waves or some sort of an object that we can viscerally imagine, that we can visualize. But the reality is, the vacuum itself is typically where all of the action takes place, not in the matter, but in the field around the matter, which extends from the matter. This could be very well the solution that we've been looking for. And if it makes sense, mathematically, it has a pretty good chance of being true. And guess what? The movement of momentum in gravitation is negative, not positive, because positive momentum would literally kick something away and you would recoil in the opposite direction. We see that exactly the opposite of that is happening. A negative momentum given off by a particle will make it move in the direction of the emission. And when absorbed by another particle, it will draw the particle toward it. Negative momentum explains it all. The thing that people find, particularly in physics, really irritating is the thought of negative energy. You know, for a long time, people didn't believe in positrons, the antimatter electron, and they didn't believe in antiprotons, the antimatter proton. But it was discovered that they were indeed real after the fact, and they only knew that it was possible because the mathematics worked. In this case, for gravitation, the mathematics works, and that should be our first lead to understanding what's happening. So, if you're interested in gravitation, there is a really good book that I recommend. It's possibly a bit out of date these days, but it's entitled Gravitation. And Kip Thorne is the fellow who did, well, all the heavy work for this book. Thorne. He is definitely one of the more interesting physicists in recent times, very popular in the 70s. And look up the book Gravitation. Give it a read. It's a thick one, I have to remind you. It's not just a little thin comic book of a thing. It's a volume. But there are many interesting concepts in there that may help clear up our thinking about gravitation if we're not familiar with the subject. So if there are any questions about gravitation, the floor is open. And meanwhile, I'm going to urge you, join us, become a supporting member of the Universe Science Center or Schultz Laboratories, and help us grow and spread the message that we're sharing with everybody about education and physics and mathematics and all the interesting things like space travel and logic gates. We're going to have courses very soon on computing, robotics, and music and mathematics. Do join us Monday evenings for those at 9 p.m. Eastern Standard Time. Go to the site and see the posted schedule, which will be up very shortly. And so I don't see any questions on the floor. I'm going to read my quote for the day, and it is, "Be strong and of good courage. Do not fear nor be afraid of them. For the Lord your God, he is the one who goes with you. He will not leave you nor forsake you." And that's Deuteronomy 31:6. Hey, have courage, take heart. Doesn't matter who your enemies are, you've got a friend who's much stronger than they are. So, with that, I don't see anything outstanding on the floor, and I think I could say many, many hours more of things about gravitation, but I think it's best at this point if you just read a little on it, see what's said, and realize you're going to run into a lot of people that say gravitation is just electromagnetic. No, it isn't. It's entirely different, and that's proven. Don't fall for the hype. There are a lot of people out there who claim to know physics or have this amazing, wonderful new theory. The physics we know came from literally centuries of experimenting and learning to find out what it is. And I have discourse with people all the time who think that they can describe the atom or the particle as something new. And all I can think of is, don't they realize we can actually see atoms and see electrons at this scale right now? We've got the technology. So it kind of blows their arguments out of the water. Believe half of what you read and none of what you hear. That's always a good rule. Well, everybody, thank you for coming in tonight and listening to the Randomizer and our talk about gravitation. And I hope that you have a wonderful evening. And I would say, my usual, make the world a better place. This is Charles Schultz with Randomizer. Have a great night, and thank you.